Hello everyone. In this video we're going to review chapter 9 and 10, which is kind of just combining all things about significance test. So again, you don't have this green inference summary to help with state plan do conclude, but I do have this and some other resources that might help you, so please contact me if you feel like you are still struggling with setting up state plan do conclude for different problems. And I can definitely send you some more resources or even do another video setting that up. But I feel like for the majority, y'all are pretty good. But let's kind of talk through, I'm not going to write it all down, but for a significance test, what do these look like? So for state, that is where you set up a HO, HA, and your significance level, alpha. For plan, that is where you check your conditions, and we normally name our test, which here it's under do, but we normally write down wherever you want in the calculator, write that down. And your conditions are, is it random, either random sample or random assignment, random treatment. If it was random sample without replacement, you need to do 10% rule. And then you need to check normality, which depending on, first, does it say it's normal? If it doesn't, if it's a proportion problem, check large counts. If it's a mean problem, check central limit theorem. And if it doesn't meet central limit theorem, then you'd have to graph it if they gave you the data. And your do, you would do it in your calculator and get these things and write them all down and label everything and make sure you named your test either in the plan or the do, it doesn't matter. And then your conclude is that format that we should all be comfortable with by now. Since the p-value is less or greater than alpha, we reject or fail to reject HO, and we do or do not have convincing evidence for HA, but you write out whatever HA was in words. So again, if you're like, I don't remember, please let me know. But for proportions, you always use Z, and I already have that written down because I messed up earlier. So just keep that in mind. So what is that talking about now? That is not Z star or T star, it's your test statistic, which if you were going to do it not in your calculator, it's the standardized test statistic. This could be Z or T, okay? But it's the same formula. So that is your test statistic. It's always Z if it's proportion. It's probably T if it's a mean, but we talked about that in the last video. Also, another thing that always needs to be true is HO is always equal to, right? If you look down here, HO is always set up with equal to. And another thing that just popped in my mind is when you set up your hypotheses, they should always be about parameters. We make a hypothesis about a population value, not a sample value. The sample value, you don't have to hypothesize about it, so it should be a true P, a true mean, mu, or just P with no hat. And so when you write out your stuff in context, make sure you're referring to your population value and not your sample value. Okay? So just be careful about the wording you use. It helps to use the words like true or population. So again, I'm not going to really walk through this. You can look through this. One thing I'm going to say is these two is like the confidence interval, the same in the calculator. It just says t-test. It doesn't say one sample. Just so you know. And then paired is when you go it's like when you use matched pairs design, and you take them all and then you get the differences, and that difference column is your data. You're not using the actual people, but the difference in the data. That's why it's still one sample, because it's one column of differences that you use to find your information. And make sure you set up, if it's a difference or two prop or whatever, you need to show the order that you subtracted in, because that's going to change stuff. If you switch it, that's fine, but you have to stay consistent through your setup. I think that's everything. The difference between these is that this is like matched pairs. I'll write this down on the side. Paired data is from matched pairs, and then you get the difference. This, if it's coming from an experiment, it's two means. That comes from like a random design, and it's just two groups. Two independent groups. And maybe like one group got one treatment and the other group got the other treatment. And they can be the same sample size, or they don't have to be the same size. With this, they have to like predetermine paired and then subtracted to get the differences. I think of this paired data is the mean of the differences. This is the difference of the means. So we always set our HO normally to be 0. And then that p-value, also that's not on here, but you should understand by now what that p-value is. You do all your work, it's assuming the null is true, the probability of getting our sample result. So if it's a small p-value, then that means the probability of getting our sample result was so small that that null probably isn't true, and that's why we reject the null if it's a small p-value. If it says pool in the calculator, just always say no, okay? You don't have to worry about that, just put no. And then let's talk about the type 1, type 2 errors. Let me make sure I added everything up there that I wanted to add. Yeah, I think we're good. So it might help if you use this chart again. I might have to go on another sheet of paper as well. And we have kind of two different scenarios. Either HO is true or HO is false. And then you have two different options. You either reject HO or fail to reject HO. So if we think about all these different, you have 4 different options. If HO is true and you rejected it, then you made a wrong decision, and what you did was considered a type 1 error. And so the probability of making a type 1 error is equivalent to alpha. Ooh, that's supposed to be alpha. I don't know what I'm doing over here. Type 1 error, which is alpha. That is so messy. I should have done this on another sheet of paper. Okay, so if you reject the null, but the null was true, you made a type 1 error. If you rejected the null and the null was false, then that means you made the right decision. And that probability of making this type of correct decision is called power. And then if HO is true and you fail to reject HO, so if you fail to reject, you never write this word down, but that's like accepting HO. So if you accept HO and HO is true, that means you made the correct decision. And we actually don't have anything for that probability. That's just good. We don't really talk about that one that much. And then if HO is false, but you, quote, accept it, you made the wrong decision, and that is type 2 error. And so the notation, this one isn't as common, but to help us relate all this, we can call it beta. It's like a bee with a tail. This is literally the same as a significance letter. Okay, that's a reason that's alpha. This one is just so we can refer to it in a second when we talk about power. Now I lost my train of thought. I don't know. So how do we talk about these type 1 and type 2 errors? Oh, that's what I was going to say. How do you memorize which one's type 1, type 2? Is if you fail to reject, it's type 2 error. So that means if you reject, it's a type 1 error, if you're wrong. Both of those, you're wrong. You made an error. The way I put these in context is I take it a step further. I don't know, if it tells you to put it in context, it's kind of hard when you leave it in terms of this. So for type 1, I know a type 1 error is when I reject HO. So what does that mean? If you reject HO, I would write for a type 1 error, I reject HO, so I had convincing evidence. For, and then I would say HA in context. But if I had convincing evidence, but I was wrong, so, but it wasn't true, or however you want to word that. You had convincing evidence for HA, but HA was wrong. Type 2, think about if you fail to reject, then you do not have convincing evidence. So I did not have convincing evidence for HA, but I made the wrong decision. I should have had convincing evidence. HA is true, but HA is true. So if you're trying to write out, this is the just definition. If you're trying to actually write it out, I would take it a step further and talk about HA. But you should know if you reject HO, you have convincing evidence for HA. If you fail to reject HO, you do not have convincing evidence. And then if it talks about consequences, you just have to read the problem and figure out kind of what would the consequence of doing this or that be. For power, so we know power is a good thing, right? Power is the probability of being correct when you reject the null. So we have to, I'm going to write it just on here because I'm running out of room. So technically, power equals 1 minus the probability of a type 2 error. I don't think you really need to know that, but it kind of helps you then to know what does that mean as you increase alpha, your significance level, you increase power. But you also increase the probability of a type 1 error, or So as you increase alpha, you increase power, which is good, but then you also increase probability of type 1 error, right? Because we know alpha is the probability of a type 1 error. So that's, you got to find the balance. What alpha is ideal to where you have a good power, but you don't have too much probability of committing a type 1 error. Another thing you can do is as you increase in your sample size, you increase power. And we know it also decreases variability, so there's no really con to increasing in. So this is our favorite. And so what do you, if it says why, is because it decreases variability, which is going to make the alternative value farther from the null. So this last way to increase power is out of your hands, can't control, but the farther away the true value is from the null, the larger power will be. And that's where we use that Khan Academy video, and we saw as that true distribution got farther away, there was less overlap. So if it ever asks why, so if it says how do you increase power, increase alpha or increase in, why do those is because it takes the true value farther away from the null and there's less overlap between this null, like hypothesized distribution, and the true distribution. So that is where I'm going to leave it for the errors in power. The last thing is, if doing a test from an experiment, we can make an inference about cause and effect because the treatment is randomly assigned, but if the subjects are not chosen randomly, we cannot generalize to all people or all population. So that's going back to chapter 4. If you look at the end of your chapter 4 notes, we did practice on the difference between random sampling and random assignment, and what does that mean for your conclusions. So So that is chapter 9 and 10. Now, obviously, we didn't like do an example or anything, so as you're working through these, please let me know. I can do another separate example video. Well, I will when I do the free responses, but if you need something else, just let me know.